In this video, we're going to look at the self-inductance of a coil through which current is running. In the last video, we looked at mutual inductance briefly, and we talked about how two adjacent or closely oriented coils of wire or loops of wire can affect each other. If the current through one changes, that changes the magnetic flux through the other. What we're going to recognize today is that even one loop of wire, if it has a changing current running through it, will experience a magnetic flux, a changing magnetic flux, due to the field of the wire itself. And so we're going to talk about self-inductance. This is really important, especially if you're doing circuits, because what are circuits but loops, right? Circuits don't work. No current flows unless the loop unless they're closed. So just by their nature, circuits constitute some sort of closed loop. And if you have several different circuits, appearing on a circuit board, then you get mutual inductance. But even if you just have one, you get self-inductance. And so we're going to need to learn to characterize this. To start, let's just talk about the magnetic flux through a coil. Right. The magnetic flux through any coil has got to be proportional to the current producing the flux. Now, if we have one coil through which a current is flowing, and that current changes, well, that current is producing a magnetic field, which necessarily is passing through the coil. And so if that current changes, then the flux through the coil also changes. And so you have the flux arising due to a field from the source current in the loop itself, right? So just the loop is, just this one loop with the current is putting a magnetic flux through itself. And if the current changes, the flux changes, right? So what we can take from that is that the flux has to be proportional to the current. If that's the case, I can run an experiment and determine the constant of proportionality. We've seen constants of proportionality all over physics. F is equal to ma is a good example, right? M is the proportionality constant that relates the net force and the acceleration. I'm going to do the same thing here. Let's assume that I run that experiment and I come up with this. And I'm going to call this constant L and then I, where L is what we call the self-inductance. Yeah. And so this would be the equation for one loop. Of course, I can generalize this through the method we've seen already. If I have n turns in this, then I can write this as n phi b is equal to Li. So this would be the case where n is equal to 1, but my general expression is this. All right, fair enough. Just for kicks, let's take a time derivative of this expression. Let's differentiate both sides with respect to time, and what do I get? Well, n is a constant, so it comes out of the derivative, but I'm going to get n d phi dt. This is phi b, of course. And then on the right side, L is the constant, it comes out of the derivative, I get L di dt. Great, well, what is this? D phi b dt is just the, I should say n d phi b dt from Faraday's law of induction is the EMF that's induced in the coil. Specifically, it's the negative EMF induced in the coil. So let me rewrite this as the EMF that will be induced due to this changing flux. I'll move my negative sign over, and I get negative L di dt. That is an important expression. Let me draw a better star. The EMF induced in the coil due to the changing current in the coil itself is negative L di dt, where L is the proportionality constant between the magnetic flux and the current, which we call the self-inductance. It also leads us to the easy way to calculate this, or at least easy experimentally, because I can run an experiment and take measurements. I always want to define L positively. Notice the current and the field have a particular direction associated with them. So that means that if I reverse the current, I reverse the field. So these are always going to have the same sign. I want to preserve that moving forward. So let me always define L positively, which is obvious here, maybe not so obvious here. So if I'm going to do that, let me just get rid of the negative sign by taking absolute values. And I'm only doing this because I want to use this expression to calculate L. So I come up with L is then equal to magnitude of the induced EMF divided by magnitude of the time derivative of the changing current, or the time derivative of the current, I should say, that involves a change. So this turns out to be the self-inductance of a loop. Now, what does this do for us? This is all the math and how we calculate it and what it means. What does it actually do physically? Oh, sorry. Well, let me introduce you to yet another electrical symbol. We've seen symbols for batteries, we've seen symbols for capacitors and resistors. I'm going to introduce you to what's called an inductor. Just looks like a coil. This is an inductor. The symbol for this will be L, just like the symbol for resistor was R. I should point out that just like when we drew a symbol for a resistor, right? I drew this. And I said, this could either mean some electrical component that you place into a circuit, or it could just be shorthand for the natural resistance of the wires as when you're moving around. Because when we draw circuits, we model the wires as resistanceless, and then usually we sum up their resistance by putting in this symbol. The same thing will happen here. This could be an electrical component that I put into the system. It could be just a symbol representing the self-inductance of the circuit itself, because just like every wire will have some resistance, as long as we're not superconducting, every circuit will have some self-inductance. And so we usually model the circuit itself as having no inductance and just sum that up with a component. But it also could just be a component you put in. All right, so what does this do? Well, imagine that you have a circuit. I'm going to put in a resistor and an inductor. This is called an RL circuit for obvious reasons. Then I have an EMF here. Let's say that I am driving current around this. So I'm coming through the resistor, through the inductor. Now, the inductor is a coil, therefore there is a changing magnetic flux. Not changing. Therefore, there is a magnetic flux through the inductor as long as the current is steady. But if I turn this off, then the current drops, right? And before we saw that the current would just stop immediately. If all I'm worried about is the resistor, if I take the EMF out of line in accordance with Ohm's law, right, the current drops immediately, or it stops immediately. But of course, in real life, that's actually not what happens. This happens beautifully on paper, but in real life, if I turn off a circuit, it takes a little time for the current to drop down to zero. The current starts to drop, but it doesn't just cut off immediately. It happens pretty fast, usually, but it does take some time to come down to zero. That time is explained by the presence of the inductor. When you turn off the current, automatically that yields a changing magnetic flux through the coil. That induces an EMF. And what does an induced EMF want to do? It wants to stop the change. So if there is a drop in the current, an EMF will be induced in this coil due to the changing magnetic flux that seeks to boost the current, right? So if I turn off this switch and the current starts to go down, an EMF is induced here, which tries to push it forward. It fails, at least in the long run it fails, but it does manage to elongate the period it takes for the current to stop. So the current does not actually stop immediately like we've been modeling it to do. In real life, the current ramps down. It decays due to the inductor. It's a decaying exponential, I should point out, due to the presence of the inductor. If there's no actual inductor, it's due to the self-inductance of the circuit itself. The circuit wants to keep the current going. What happens if no current is flowing and I flip the switch and put the battery in line? The same thing, but in reverse. As the current starts to ramp up, an EMF is induced in the coil that strives to oppose it. It also fails, right? But it also, but it does succeed in changing the shape of the current with respect to time. So we can immediately draw some graphs. If I turn the switch on, the current starts to ramp up and eventually gets to the full current. But the shape of this curve is determined by the inductor. Similarly, if I turn the current off, it starts at some value and then it decays down and eventually gets to 0. Again, because of the shape of this. Before, when I was just considering Ohm's law and didn't worry about inductance, if I flipped the switch, the current started here immediately, right? We've seen behavior like this, though, with capacitors, with RC circuits, because the capacitor takes a little bit of time to charge, and that has the effect of changing the shape of that initial current when you start and when you stop. Inductors will do the same thing for different reasons. We're not charging a capacitor, but we are inducing an EMF which opposes this EMF and takes a little bit of time to overcome. So that's what inductors do for circuits. Again, we like these in circuits for the same reason we liked capacitors. I mentioned because a capacitor takes time to charge, and because its time constant is only based on macroscopic parameters, R, the resistance of the circuit, and C, the capacitance, which is determined by physical characteristics, area and distance. Because of that, they're really easy to use for timing circuits. Same thing will happen here, because this will have some sort of characteristic time, right? Which, as you can probably imagine, will involve R and L instead of R and C. Then I can create timing circuits with these two, and the time constant just depends upon physical parameters of the inductor. We'll see that in some examples, but for now just hang on to the idea that this is what an inductor does in a circuit. This is self-inductance. It changes the shape of the initial and of the beginning and ending currents very similarly to how a capacitor changed those shapes.